Assembly programming isn't hard. What makes it hard is the requirement to make a mental paradigm shift in order to internalize the structure of assembly language. I learned assembly when I was a schoolgirl. It was a long time ago, and I still remember how it clicked for me. The thing is, for someone who is learning assembly right now, the same click of understanding may be much more difficult to achieve and take longer because of how computer systems have evolved, because of all the many layers of abstraction that appear between the programming interface and the low-level interface. In this video, I'm going to show you exactly what I saw and how it clicked for me. But before it can happen, we need to debunk some myths. This was just myth number 1, that assembly programming is hard. Myth number 2 is that assembly programming is irrelevant. This couldn't be further from the truth. And the truth behind this myth has two sides. One side is that assembly language, low-level programming, is directly used in many situations and scenarios in computer science, in computer industry. One example is, of course, shell coding, which is used in binary exploit development, my specialization. Another example is optimization. Optimization is a broad field which applies to many different areas of coding and software development. For example, audio and video processing relies on optimization a lot. JavaScript engines and browsers require optimization as well. So whenever there is a need for optimization, assembly programming comes in because it really is the fastest way to get anything done on the CPU. Another side of the reality behind this myth is the cluster of situations where assembly programming isn't used directly, but rather the basic principles of how it operates are used. These are the situations, mostly in programming, when we use low-level concepts to develop the software, such as bytecode VMs that are extensively used in Java and JavaScript, as well as other interpreted languages. Also, the same low-level concepts are used in computer graphics, OpenGL, as well as in low-level language, which is used when programming GPU directly. Basically, in all situations where speed is involved, where optimization is involved, you will find assembly programming. Myth number 3 is that various assembly languages are very different, and one may be more important than the other, and one may be more complex than the other. As you will see, first off, the structure behind all assembly programming languages is the same, which is the main thing. And then only the labels, the names of the mnemonics are actually different. The names of the registers, the names of the mnemonics. Nowadays, there are multiple CPU architectures which occupy their own niches, and therefore not one of them is dominating or extensively more popular than the other or better successful. Each architecture found its own place in the ecosystem and they coexist, which also means that if you want to become a great hacker, you will sooner or later need to learn all of them. The most dominant architectures currently and their respective assembly languages are x86, which dominates desktops and server-side equipment. Then there is ARM with several different flavors to it, which dominates mostly mobile market, mobile devices, and also a little bit of the IoT. Then there is RISC-V, which is a newer one, and it is growing very, very quickly, and it is poised to dominate both mobiles and IoT, and it will go into desktop and server as well. And lastly, there are more minor architectures like MIPS and Hexagon, some others. All of them are currently used. All of them can be found in software that you're about to hack, so you will need to be familiar with it. My point here is that the structure behind all assembly programming languages is the same. It means that if you think at this level, at the level of the structure, which is what I'm talking about in this video, then it will be very easy for you to switch between different assembly languages and learn them all at once or very quickly learn another one. In my personal experience, the assembly programming languages which I learned was x86 32-bit, which was basically the only one and the mainstream language back then. And then when I started working as a malware analyst, and I had a night shift job, and we need to process malware samples, analyze them within the given time, within the night. So occasionally I would receive a malware sample in unfamiliar architecture. And because of the internal competition that existed in the antivirus market, I had to learn that new architecture, new assembly language within one night, because I had to completely analysis and publish the blog post. So that is how I basically learned all the other assembly architectures. I learned ARM that way, and I learned MIPS. There were some other minor architectures that are mostly irrelevant now. It took me about one night to both learn to make this shift from the x86-32 to another architecture, to learn it enough to at least understand what is going on in the code, and then to analyze the actual sample. You get the idea. If you get to the right level of learning a system, then you can learn multiple superficial varieties of it quite quickly. So I would say that the difference between assembly languages is much, much smaller than the difference between Hispanic languages. It's just mnemonics. Everything is the same. You just have to replace one mnemonic name with another mnemonic label, and one name of the register with another name of the register. That's it. Myth number 4, assembly languages are eternal, unchanging, timeless, and cast in silicon and metal. Well, part of it is true, part of it. But mostly I want to show you the reality, which is quite different. The reality is that assembly language is just as evolving as anything else in the computer ecosystem, anything else in technology. It is evolving a little bit slower, but the evolution is still there. So there are two sides to this evolution. One side is that new assembly programming languages get introduced because new CPU architectures get introduced. This process is driven importantly not only by marketing competition, but also by the requirements of the new technology emerging. For instance, AI models nowadays require a completely new architecture in order to provide optimized execution environment for both neural learning and inference. Hardware developers keep coming up with new CPU architectures and also with their own new assembly programming languages. Now, the second part of the reality behind that myth is that aside from the evolution of assembly programming as a field by introducing new languages and new architectures, also programming languages themselves keep evolving. Hardware developers keep evolving their own architectures and their own assembly programming languages when they introduce new hardware features. So if you follow, for instance, Intel development manuals, which I do for many years, and it is interesting to see how each new cluster of hardware technology introduces a new cluster of respective assembly programming instructions and logic. Another important aspect of this is that assembly language nowadays isn't really entirely cast in silicon. So there is only some basic, very, very basic level of CPU operation, which is cast in silicon and metal. Above that, there is the firmware called the microcode, which consists the actual logic of the assembly instructions. Microcode is one level deeper than assembly programming, but it follows the same structure. So if you understand assembly, then you will easily understand microcode. The problem with microcode, however, is that it is completely closed source and it has to be reverse engineered from scratch. Just as any technology which the development of it is accelerating, so the same applies to assembly programming. There is more and more new features added into your favorite assembly language, and then there are new assembly languages appearing in the industry, in the field, that gain considerable relevance, and you have to know them as a hacker. However, the core of it stays the same. And by core, I mean overall structure, which is the same for all assembly programming languages. And then also the core of the assembly syntax also stays the same. The basic instructions in the assembly will never change because software relies on it for compatibility, which means that if you learn the core of the assembly language, it definitely will stay for years and decades, and as long as the architecture is relevant, it will serve you. First thing that you need to understand is the overall principles upon which assembly programming and assembly instructions, assembly languages are built. There are three general principles which apply universally to any assembly language and any assembly programming experience. Principle number one is that assembly consists of simple, primitive, trivial instructions or expressions. As human beings, we use natural language to communicate, and high-level programming languages such as C++ or JavaScript are actually modeled after natural languages. And natural languages are expressive. A single expression can be quite complex. For example, if you think of a statement in high-level programming language which calculates some simple mathematical formula, all the calculations can be done on single line within one single statement. However, assembly programming is different in that it consists of simple atomic operations. Each operation just does only one thing, and it is a very simple thing. If you look at an example assembly program in any programming language, you will see that it consists of this kind of basic primitive operations. The first word in that operation is the instruction itself. What do you want to do? Move, add, multiply, call, jump. Then there is usually two or more operands to which the instruction that you refer to applies. There are several classes of atomic operations in any assembly language. One big class of such operations are arithmetic operations, which include addition, multiplication, subtraction. Another big class is control transfer instructions, which include simple primitive instructions to jump to another place in the program, to transfer control of the CPU to another spot. It may be jump or call. They're a bit different, but at this point the difference is irrelevant. And then there is a big cluster of instructions which simply moves things around. Move a value from one register to another register, or from one piece of memory to a register, or something like that. There are also other classes of instructions which are more complex and specialized. So you can think of these three large classes: arithmetic instructions, control transfers, and moving instructions, moving data. In fact, if you look at any modern program written in assembly programming or reverse engineered back from the high-level programming language to assembly, majority of instructions will fall into one of the three classes. Even the modern and complex programs mostly use very primitive, very trivial instructions in the assembly. Principle number two. In assembly programming, everything that you work is memory. Okay, not only memory, there are also the registers. The registers are special spots inside of the CPU. They are literally in the hardware, and these little slots have fixed width, which is the same width as the architecture that you're working on. So most modern architectures are 64-bit, which means that registers that you work with have width 64 bits or 8 bytes. So in assembly programming, you only ever work with either memory at large or the registers. In high-level programming, you have variables, you can have arrays, you can even work directly with functions, do something with them, get some pointers. In contrast, in assembly, you only have low-level access to memory, which is like a huge field. It is unstructured, and it is up to you as a programmer to structure it and to access the spot that you need. So most of the assembly instructions work with registers, but some of them also work directly with memory. And what happens is that when you need, for example, to do some arithmetic operation, you can take an immediate value, which is an integer, for example, and you can add it to some value inside a register. And then you can put that value from that register to some spot in memory. And important thing is that operations are atomic, so you cannot do all of these things at once, as you would do in high-level programming language. Rather, you will need separate assembly programming statement for each part of this operation. This is part of the reason why assembly programming appears complex, that it is so atomic and low-level. And what you would normally accomplish with just one large statement in high-level programming, you will need a whole little program of assembly instructions to accomplish the same thing. And this is one of the points of complexity in assembly, that you need to kind of reassemble this set of little instructions in your head to achieve the high-level operation that you're thinking about. Because everything in assembly is memory, it is up to you to create a structure in memory that you will be working on. If you're looking at the string, you're searching for a null byte in it, then you need the address of this beginning of the string in memory. Then you will add 1 to it to address the next character. Then you need 1 again, and you will add 1 again to address the next character, and so on and so forth. One by one, you will access each character of the string. And all of that, sounds very trivial in high-level programming, but in assembly, it will take quite a few designated instructions. And principle number 3, all the input and output is done on the low level. So in high-level programming languages, if you want to print something on the display, you have usually some sort of API that is given to you by the operating system that you can call and just give it a string and tell it, just print this string in this place, in the title or whatever. In assembly, however, the I/O is low level, meaning that you will be directly working with low level aspects of hardware in order to output your data to the monitor or elsewhere, as well as to read what you need to take from the keyboard, from the mouse. The next thing you want to understand is how output works in assembly programming. Let's say you have calculated something in assembly programming, in your assembly program. You have taken out some values from the memory. Next, let's say that you want to print out the contents of the file on the display. A display or computer monitor has a designated piece of memory attached to it, so to say, which is called a frame buffer. A frame buffer is a special buffer or a piece of memory starting from a specific address, ending at a specific address of a particular length, which represents the pixels on your monitor. And now I'm going to simplify this a little bit, so in reality it doesn't have to be implemented exactly in the same way, but the principle is the same. You have to do calculations, arithmetic calculations, to figure out which is the offset of the pixel that you are addressing, set that pixel to the desired value, then calculate the offset of the next pixel, and so on. In this way, you can draw or write anything that you want on the display. And this is exactly what happens underneath all this complexity that you see on the computer screen. It's usually handled by kernel mode drivers of the operating system, which are responsible for abstracting away those low-level aspects of graphics and video. And this is so amazing. If you look for some time at these programs and you study them for a little bit, then you start perceiving the 3D world differently. You don't see it as a common picture that we're familiar with, but rather you start seeing more of math formulas and pixels behind of this graphical picture that you see. It's similarly like assembly. When you do assembly long enough, it will change the way how you see the world. There was a comment in my previous video, somebody he said, so I'm a web designer, quote unquote, and I love it so much, and I don't understand why. I just want to do assembly. Assembly is very close to reality. In assembly programming, there is this small, compact set of trivial basic instructions from which you can build a very complex logical program. This is very similar to how the world works. Anything that you look at, any system, has some sort of a small set of basic primitives underlying everything, from which everything else can be deduced logically or somehow produced. So that is the reason why you like assembly so much and your mind loves it. So if you do assembly long enough, it will change the way you think. If you look at any objects or any social interactions, you don't see the face value of it, but rather you immediately go deeper and see the low-level primitives of which it is made of. You won't react to things or events in the same way as before. You will not be able to engage in social interactions in the same way as before. Your focus is much deeper than the focus of another person, of an average person, and basically you go out of touch maybe with the normal world. But you have to do assembly for quite a while, I think at least for 1 month, in order to change your mind in this way. Lastly, I want to mention how input works. So we have the basic principles, we have the output to the display, and then we also need the input, or how do you actually read what is printed on the keyboard or get the signal from the computer mouse. I will explain this very briefly. It basically works in the same way as with display, except that it works the other way around. You can imagine that a computer keyboard has a specific buffer attached to it, which is mapped onto the memory. And each time when you press a key on the keyboard, it will represent one bit in your memory, in this buffer, which represents the keyboard. Now, you can have an assembly program which simply looks at this buffer, it goes through it over and over again, and notices if there is any bit which has been set. And based on the offset of that bit from the beginning of the buffer, you will know, or your program will know, that a specific key on the keyboard was pressed. So this is again a little bit of simplified picture, and in modern systems it works a little bit differently, but the overall principle is very common and is used across a variety of different input and output devices. With these three pieces in place, the assembly principles, universal principles, the low-level principles of output and low-level principles of input, connecting these three pieces together, you should be able to pick up any specific assembly programming language, as well as to imagine or visualize how the software that you're working with, how the user interface that you're looking at works behind the scenes on the low level.